everyone, and welcome back for another deep dive. Today, we are going to be pushing the boundaries of what we think we know.
Mm.
We're talking geometry, and then information flow, and even consciousness itself.
Whoa.
Our main source is this research paper called Bridging Geometry, Consciousness, and Mesoscale Coherence, a unified approach.
Okay.
We've got some supporting material, too. If you've ever wondered how these totally different fields could even connect, you are in the right place.
Yeah, it's really fascinating how this research kind of brings all these different concepts together. It all starts with this idea called integrated information theory. You might have heard of it.
IIT?
Yeah, IIT. And that explores how consciousness could emerge from the way information is integrated within a system.
Okay, so IIT, I mean, for those of us who are just tuning in, basically it says that the more interconnected and integrated the information is within a system, the more conscious it is.
Right.
But how do you even measure that? How do you measure consciousness?
Yeah, that's the big question.
And this is where the research takes this really interesting turn. They use a specific geometric shape as a model to study this.
Yeah, they chose this shape called the small stellated dodecahedron.
Mm-hmm.
There's this complex kind of 12-pointed star made up of all these even smaller interconnected star shapes.
Whoa.
It's a really beautiful structure when you look at it.
I'm looking at a picture now. Yeah, it is.
And it really embodies this idea of information integration because each point in the shape is linked to the other points in a very specific way.
So they didn't just choose any random shape. They chose it for a very specific reason.
Yeah.
And they actually created an algorithm to generate smaller and smaller versions of this dodecahedron. Is that right?
Exactly, yeah. Each iteration of the dodecahedron represents kind of a different level of information integration within the system.
So it's like those Russian nesting dolls, where you have one inside the other and they're all slightly smaller.
Yeah, that's a great analogy. It's this recursive structure where you see the same pattern repeating itself at all these different scales.
Mm-hmm.
And it's not just some mathematical curiosity either. We see recursion everywhere in nature. I mean, you see it in the branching of trees, you see it in the patterns in seashells.
Even in our own thoughts, right? The way we build upon ideas and we connect these smaller concepts to form bigger ones. It's all connected.
It really is.
But how do they actually quantify the level of consciousness in this model using the dodecahedron?
So that's where this idea of phi comes in. It's
Well,
represented by the Greek letter AFI.
okay.
And they calculate this phi value using an algorithm.
Mm.
And it represents kind of the level of consciousness based on how integrated the information is within that specific version of the dodecahedron.
Okay, so the more integrated the information, the higher the phi value and the more conscious the system.
Exactly.
But how do we even begin to understand what that means in the context of a shape? A shape isn't thinking, right?
Well, yeah, that's a great question. It's important to remember that this is just a model, right? It's just a way to kind of visualize and study these really complex concepts. Think of it like a map. You know, a map isn't the actual territory, but it helps us navigate and understand the terrain. And in this case, that terrain is consciousness. And the map is this kind of geometric representation of information flow.
Okay, I'm starting to get the big picture here. I'm starting to see how they're trying to map this out. But this research paper also throws another kind of element into the mix, which is this formula, T equals H times B.
Right.
And math is not my strong suit. So can you kind of break this down for me a little bit? What does that even mean?
Yeah. So essentially, that formula describes how observable phenomena, the things we can see and measure, emerge from structured states when they're influenced by these tiny little changes or perturbations.
So a ripple effect.
Yeah.
One tiny change can cascade and impact the whole system?
Exactly. Think about a house of cards. So that's like your structured state.
Yeah.
Now imagine just a slight breeze, a little perturbation, and how that can cause the whole thing to collapse. That's what that formula is getting at.
Okay, yeah. I can see how that kind of applies to physical systems. But how does it connect to the dodecahedron and consciousness?
So to study how that dodecahedron evolves over time, they use something called a Mealy machine.
Mm-hmm.
It's basically a computational model that represents how the system changes from one state to another based on different inputs.
So the Mealy machine is a simulation of the dodecahedron's evolution, showing how its consciousness changes over time based on different factors.
Precisely. And here's where things get really interesting. They found that the growth function of this Mealy machine, the way it evolves over time, exhibits this thing called polynomial behavior. Essentially, it follows a specific mathematical pattern as it grows.
Polynomial behavior. Okay. Can you remind me what that means?
Yeah, so think of it as a way to describe how something changes over time. For example, if you have a plant that grows at a constant rate, we could represent that growth with a simple line on a graph, right?
Okay, yeah,
That's linear growth.
got it.
Polynomial growth is a little more complex, so the line on the graph curves because the rate of change isn't constant.
Okay, that makes sense. But the research paper mentioned something about irrational degrees in this polynomial growth. Like, what does that even mean?
That's a really fascinating detail. So in simple terms, irrational refers to numbers that can't be expressed as a simple fraction, like pi, for example.
Okay, yeah, I know pi.
What's remarkable is that these irrational degrees are showing up in the way this system that's representing consciousness, is evolving. So it suggests a level of complexity that's, far beyond what we might expect.
Whoa. Okay. So we've got this geometric shape representing consciousness, this formula that describes how systems change, and now this like mind-bending concept of irrational numbers governing how the system evolves. It's like we're peeling back the layers of an onion, and each layer is more complex than the last.
Yeah, and we're just getting started. From here, the research dives into something called mesoscale coherence and how that could actually be applied to technology.
Okay. Let's pause there for a moment and take a breath. This is a lot to process.
So mesoscale coherence. Basically, it's this principle of organized behavior that happens at a specific scale.
Okay, I'm picturing like a flock of birds all moving in sync. Is that kind of what we're talking about?
That's a perfect example. Each bird is acting independently, but somehow they all move together in this incredibly coordinated way. That's mesoscale coherence in action.
So how does a flock of birds relate to this research on consciousness and geometry? Like, how do those things connect?
So the research basically proposes that this principle of mesoscale coherence, this organized behavior, could be the key to understanding the super complex interactions happening within that dodecahedron model we were talking about. It's like the interconnectedness of all the points in that dodecahedron mirrors the synchronized movement of the birds in the flock.
Okay, so I'm seeing the connection now. But this research doesn't just stop at describing it. It goes on to explore how mesoscale coherence could be applied to, like, circuit design. And that's where things get really interesting for me. I mean, are we talking about building actual devices based on this principle?
Absolutely, yeah. The research highlights three kind of exciting areas of application: optomechanical circuits, phononic waveguides, and automated biological systems. Let's start with optomechanical circuits.
Okay, optomechanical sounds kind of complicated. Can we break it down a little bit?
Yeah, it's actually simpler than it sounds. Optomechanical circuits combine light and mechanical motion. So think about it this way. You have a tiny vibrating mirror, and it's interacting with light beams. By carefully controlling that interaction, we can create these incredibly sensitive measurements.
What kind of measurements are we talking about here? Give me an example.
Well, imagine a sensor so sensitive that it could detect the faintest vibrations, like those caused by gravitational waves rippling through space-time. That's the kind of precision we're talking about with optomechanical circuits.
Wow. Okay, so that's like seriously impressive. What about those other applications, the phononic waveguides and the automated biological systems? What are those all about?
Phononic waveguides are super fascinating. They're basically manipulating sound waves, but at a microscopic scale. So imagine being able to control sound with the same precision that we control light today.
So we're not talking about like turning up the volume on our headphones. We're talking about controlling sound waves at like the level of atoms.
Exactly. The possibilities are kind of mind-boggling. Imagine using sound waves to manipulate individual cells or molecules or transmitting information in a completely new way.
It's like science fiction is becoming reality.
Okay, so what about those automated biological systems? What potential do they hold?
Yeah, these systems are all about interacting with like biological processes in real time. So imagine a biosensor that's constantly monitoring your blood sugar levels and it automatically adjusts your insulin delivery, or a drug delivery system that targets specific cells in your body so it minimizes side effects.
So we're talking about a future of personalized medicine where treatments are tailored to your own individual needs. I mean, this is incredible stuff. But I'm still trying to wrap my head around how all of this, the geometry, the information theory, the mesoscale coherence, even the spiritual dimension that's mentioned in the paper, how does it all fit together? Well, that's the beauty of this research. It challenges us to see the connections between all these things that we might normally think of as separate. It's pushing the boundaries of our understanding of consciousness, technology, and, the universe itself.
We've covered so much ground already, but there's one more piece of this puzzle that I think we need to talk about, and that's the quantum Fourier transform, or QFT. Can you give us a quick rundown on what that is and how it fits into all of this?
The QFT is basically a mathematical tool that's used in quantum computing. It allows us to analyze quantum states, which are fundamentally different from the classical states we're used to in, our everyday world.
Okay, so quantum states are like a whole other set of rules, a different way of looking at the world.
Exactly. And the QFT gives us this way to translate between these two worlds, to understand how these quantum phenomena might relate to the systems that we can observe at a larger scale.
So are we saying that this QFT could help us connect the dots between like the quantum world and the world of consciousness and information flow that we've been discussing?
That's the idea. It's still very early days, but the researchers believe that the QFT could be this really powerful tool for modeling and understanding these complex interactions within the systems that we've been discussing. It's like having a whole new lens to view the universe, a lens that allows us to see things we couldn't see before.
So I think I'm starting to see like how all these pieces fit together. We've gone from this geometric model of consciousness to the potential of mesoscale coherence for like building actual technology. And now this quantum Fourier transform, this tool that might bridge those worlds. But where do we even go from here? I mean, what are the next steps with all of this?
Well, one of the most exciting things to think about is exploring these real-world applications. Like, imagine if we could use these insights to develop brain-computer interfaces that would allow us to control devices with our thoughts.
I mean, that sounds like something straight out of science fiction.
I know.
But it could be incredibly beneficial for a lot of people, especially people with disabilities.
Absolutely. Think about the possibilities for someone with paralysis or individuals who are unable to communicate verbally. We might be able to give them completely new ways to interact with the world.
Yeah. And then there's like the whole field of AI. If we can really truly grasp these principles of consciousness, could we create AI that isn't just intelligent, but actually like possesses some form of consciousness?
That's a question that researchers are actively exploring right now. And it raises all sorts of ethical considerations.
Yeah.
Like, if we create a machine that's capable of experiencing the world in a way that's similar to humans, what responsibilities do we have towards it?
It's mind-blowing to think that we might be on the verge of these kinds of breakthroughs. It's like we're standing at the edge of this vast, uncharted territory, and we don't know what we're going to find.
It's true. And this research just opens up so many possibilities. It makes us reconsider our assumptions about technology, about consciousness, even what it means to be human.
This whole deep dive has been one giant aha moment after another. I feel like I've got this whole new perspective on how everything is interconnected. From the tiniest quantum particles to the vastness of the universe, it's all connected.
Yeah. And that's really the key takeaway here. This research isn't just about understanding these individual concepts in isolation. It's about seeing that bigger picture. It's about recognizing this intricate web of connections that make up, the fabric of reality.
I have a feeling we've only just scratched the surface of what's possible here. There's so much more to explore and understand.
Exactly. And I hope that this deep dive has sparked your curiosity and inspired you to keep learning and keep exploring these ideas.
The pursuit of knowledge is a journey, not a destination, so keep asking questions, keep exploring, and who knows what incredible discoveries you might make along the way.
Until next time, keep those brains buzzing.